Hello everyone, my name is Benedict Bahr-Kalus and I've been a postdoctoral researcher in the cosmology group at the Korea Astronomy and Space Science Institute for a bit more than half a year. The topic of my talk today is the Kaiser rocket effect, and it is the fruit of a project I started with Daniele Bertacca, Licia Verde and Alan Havens when I was still at the University of Barcelona. By the time you're watching this, we hope that you can find the preprint of this paper already on arXiv. So if you're like me, you might not associate the term Kaiser and rocket with cosmology at first. So let me start with what the Kaiser rocket effect is. If you attended last year's edition of Cosmology from Home, there was a great talk by Aaron Glanville about the effect of systematic redshift biases on BO cosmology, and you might be familiar with some of what I'm going to say in my introduction. If you don't remember that talk or you didn't attend the meeting, let me remind you that surveys do not actually measure 3D positions of objects, but angular positions and redshifts, and that the telescope is either mounted on Earth or is orbiting somewhere in our solar system, so not addressed with respect to the universe. Please excuse this sloppy expression, but I hope you get the idea. This motion with respect to the universal rest frame is often not, or only partially, or sometimes even incorrectly accounted for, which introduces systematic shifts in redshift space. Calling the peculiar velocity of the observer v in natural units, the observed redshift of an object that is at an angle theta with respect to the direction of the observer's motion is then given by this formula, which can be found in this paper by Davis, Hinton, Howlett, and Calcino. So assuming an isotropic radial selection function n of z, which is commonly done when it is inferred from the data itself, at first order we can write the apparent number count in this way. For simplicity, I'm only showing you the expression for the full sky. We get some additional terms if the radial selection function is estimated from a patch of the sky that is not symmetric around the observer's motion. Transforming that into an over-density field, that is the density field, the density contrast of the observed n hat of z with respect to the true n bar of z, we can see that this leads to spurious density fluctuation that depends on the dipole velocity and the log derivative of n bar of z. What does that mean for cosmological measurements? A common summary statistics in galaxy clustering analyses is the Cartesian 3D power spectrum. Therefore, even though it is not the most suitable statistic at large scales, we are focusing on Cartesian 3D power spectra as they are very commonly used. Having modeled the spurious Kaiser rocket density contrast, we can compute the additional power due to the rocket effect, which is proportional to the square of the dipole velocity, and is otherwise this ugly interval over radial derivative of the logarithm of the selection function and combinations of Bessel and trigonometric functions that couple the redshift space distances S prime, the wave number k, and mu. The power spectrum that an observer ignorant of their own motion will observe is then the sum of the cosmological power spectrum, this rocket power spectrum that I've just did out is this integral, and the cross power spectrum as the density field itself sources the velocity of the observer. However, we found that in simulations, this cross correlation is small, and we therefore can safely neglect it here. As the rocket power is hard to compute analytically for most realistic configurations, we are using random catalogs, which we would use for any data analysis anyway. And there are catalogs of objects that are drawn according to the angular and radial selection functions without any clustering. We are then transforming the true redshifts to the redshifts an observer in motion would measure under the effect of the Kaiser rocket, and measure the power spectrum from this shifted clustering-less catalog. For the results that I present here, we assume that the observer's bulk motion is entirely described by the CMB dipole measured by Planck, and we assume a Gaussian n of z that is inspired by Euclid as an example for a stage 4 survey. In magenta, you can see the rocket power spectrum if we could observe the whole sky with Euclid, or a Euclid-like survey. For a top hat selection function, one can easily show that the rocket power is described as the sum of Bessel functions. And for our Gaussian example here, we can still notice a clear oscillatory behavior because of that. However, no survey observes the entire sky, and we used the random catalog approach to estimate the rocket power for a masked Euclid-like survey. As you can see, the convolution of the power with the mask washes out the oscillatory features, and we end up with the rocket power spectrum that grows as we go to larger and larger scales. In the top panel, we also show the systematic to noise ratio. In the full sky case, the signal from the Kaiser rocket dominates the noise by up to a factor of 6. When we mask, apart from smoothing the oscillations, another point that we have to consider is the direction of the observer's motion with respect to the mask. In the case of a Euclid-like observer in motion, consistent with the CMB dipole, the signal reduces to just the noise level at the larger scales. Now, the question for us cosmologists, should we care about the systematic effect that can cause an enhanced power spectrum that grows as you go to larger and larger scales? I would say that we definitely should if we want to probe local type primordial non-Gaussianity using the scale-dependent bias effect. On the same assumptions as in the previous slide, and that there is no primordial non-Gaussianity, a Euclid-like survey would still measure an FNL of about 2.2. That's about 1/4 of a sigma, which is at the level where people should worry about the systematic, considering that you always have several systematics, and if they're all at a similar level, they add up to something that is far from the truth. I should also emphasize that this is not as bad as it could be, because the direction of the Planck dipole is only at the edge of the Euclid footprint, and the footprint that would cover more area in directions where the Kaiser shift is strong would also increase the Kaiser rocket signal. And also because we assumed a smooth Gaussian n of z, and as the signal depends on the log derivative of n of z, any additional features would also increase the impact of the Kaiser rocket effect. So here we have a map where we outline a Euclid-like footprint in gray, and we show the expected bias in measuring FNL if the direction of the observer's motion points towards the center of the respective field pixel. We would be surprised if the direction of our peculiar motion was very different from the direction of the CMB dipole, but it's still an interesting map considering that some corrections for the peculiar motion might have been done. And as there is some uncertainty in our motion, we might well end up with a residual dipole that can have an arbitrary direction. As you can see here, our Euclid-like survey does not cover a lot of area around our assumed motion dipole. But if the dipole is pointed towards the center of our survey footprint, we could see that we could see a 3 to 4 times larger effect. Another question we want to answer is how we can be sure whether all velocity components of the observers have been accounted for. We have identified a telltale sign of that. What that is, if you do redshift tomography and measure your parameters in each redshift bin, not only will you find the redshift dependence of otherwise constant parameters, which could also be due to various other observational effects, but also will your parameter have an extremum at the same redshift as the peak of your n of z, because there the log derivative vanishes and thus the Kaiser rocket effect becomes minimal. As the Kaiser rocket effect is a function of both the angular and radial selection, it would be unwise to focus on Euclid alone. So what about DESI? The DESI footprint in the galactic south, which you can see here in light gray, is almost aligned with the CMB antidipole. And the DESI collaboration has already published its preliminary target selection, which we show here in the top panel of the right-hand plot. And here in the bottom panel, you can see the log derivative of the radial selection function, which has a lot more features than the smooth selection function we assumed for our Euclid-like survey, and can therefore show a stronger rocket signal. And this is indeed reflected in the DESI rocket power spectra. The rocket power spectrum is larger in the galactic south than in the north. Furthermore, the rocket power spectra in the north have a turnover that makes them less likely to be confused with an FNL signal, but in the south, it very much looks like FNL. The LRG and ELG selection functions have quite strong features, and they both have a stronger rocket signal than the relatively smooth quasars. However, this does not translate directly into systematic shifts in FNL, because the different samples have different biasing laws. In the end, the expected systematic bias on FNL measurements due to the Kaiser rocket effect, assuming an uncorrected CMB dipole, ranges from as little as 3.8 or a fifth of a sigma for quasars in the galactic north to 71 or 2 sigmas for emission line galaxies in the galactic south. So as you can see, the Kaiser rocket effect is a systematic effect that may or may not dominate your cosmological inference, but it's definitely there, and it is well defined and can be easily accounted for, and therefore we also should. Here you also see the plot that I showed earlier for Euclid alone. So you see also for DESI that for LRGs, you have a very quite smooth NOZ at low redshift, and there's this big spike, and you can see this also reflected in tomographic FNL measurements. So you have basically no FNL shift at in the lowest 3 redshift bins, and then a peak at the highest one. And then for EOGs, you have oscillations all over the place. And you see in the tomographic FNL analysis that you always have a large bias in FNL. So in the rest of my talk, I'll present 2 tests that we do on Gaussian random fields. The first one is to show you that we can easily account for the Kaiser rocket effect with various mitigation techniques. And the second one is to convince you that our basic assumption of independence between the cosmological power spectrum and the Kaiser rocket effect holds, even though our peculiar motion is sourced by the density field. So first, how can we get rid of the effect from the Kaiser rocket effect? In this plot, you can see in blue the fractional difference between the power spectrum that we measure from Gaussian realizations where we apply the Kaiser rocket effect, and the null power spectrum that we measure from the same simulation before applying these shifts. You can see that we have a power excess at large scales. If you are sure that no redshift corrections have been applied before, and you are convinced that our peculiar velocity is fully given by the CMB dipole, one can follow the most naive way, but in this case also the most effective way, as you can see here in magenta, where the power spectrum agrees well with relatively small errors with the null spectrum. This magenta line has been obtained by taking the measured redshifts and shift them back to where they should be if there was no rocket effect. In any other case, for example, because you're worried that radio surveys, for example, find a motion dipole that is consistent with the direction of the CMB dipole, but don't match its amplitude, You can marginalize over Kaiser rocket amplitude elegantly by using MOTIO projection, where you add to your covariance matrix the outer product of your systematic template with an infinite amplitude. The inverse of this updated covariance matrix actually converges to something finite, and you can use that in your favorite covariance-based estimator, such as the quadratic maximum likelihood estimator. However, these estimators tend to be computationally expensive, but luckily there is something called mode subtraction, where you subtract off your template with a maximum likelihood amplitude. This will give you, in principle, a biased estimate of the power spectrum, but you can check some of my previous work to find a prescription to do this in an unbiased and efficient way. In this way, one can also marginalize over direction by using an orthogonal set of templates with different varying amplitudes. Doing so, we find the green line that is also consistent with the null spectrum, just with larger errors that account for our possible ignorance of the dipole amplitude. Finally, I still have to convince you that we really can model the Kaiser rocket power spectrum independently from the cosmological power spectrum. To that end, we used the continuity equation to compute the velocity of each point in our realizations of the density field, and we placed 2 observers into each simulation box. One observer is positioned at a random position that we choose to be the center of the box. The other observer is positioned where the velocity is the most similar to one that we measure from the CMB. Both observers then select objects for the surveys in the same way, and both observers measure their power spectra before and after applying the rocket shifts. In the plot here, you can see the residual compared to the Planck-like observer case of the power spectra of the difference in density between shift and unshifted objects of observers placed at the random position in magenta, and those placed at positions where the absolute value of the velocity field is most similar to the dipole amplitude measured by Planck in black. The error bars have to be understood as for a single realization, since that is what we can observe in reality. And you can see that the difference from assuming the Kaiser rocket effect to be independent from the clustering is smaller than the error that we have on our clustering measurement. So I hope I convinced you that our peculiar motion introduces a spurious clustering signal that we call the Kaiser rocket effect, that this signal can mimic a positive FNL, and that depending on the survey mask and the radial selections, the Kaiser rocket may or may not dominate your measurement. But as I said before, the effect is there, it is well defined, and can be easily accounted for, and therefore should. Thank you for your attention, and I'm going to look forward to your discussions and questions.